Daily lesson 210, finally! I feel like I've tried to do this twice. Now we're like, yes, let's do it. Okay, so all of this page is something that you've actually done before in some way, but it's connecting all the things that you've learned about particle motion and making sure you understand them. So we get to go back to Riemann sum. And remember, Riemann sums and trapezoidal sums are ways for us to evaluate integrals, well, at least approximate integrals. So here it says the table above shows velocity, and it's given in meters per second. So velocity, and if you want to write it up here so you know this is meters per second. Time then would be in seconds. You can feel free to do that just so you kind of have an idea. This is seconds, this is meters per second for t, and then v of t. And it's a particle moving along the x-axis, and we've got time seconds. So we did this. So this doesn't actually even ask you what this is, what value it is. All it asks is, what does this represent? And so I want you to think about this. If I have 0 to 18 of v of t dt, you could do the area under the curve, or the other thing you could do is p of 18 minus p of 0. I'm not actually figuring out what that is. I'm just thinking about it in the antiderivative of velocity as position. So 0 to 18 v of t dt represents what? The change in position from 0 to 18 seconds. And you could say this is the change in position in meters from 0 to 18 seconds. You could say net distance. That would be okay. So you could say the net distance from 0 to 18 seconds. That would be okay. But this is the change in position from 0 to 18 seconds. That's all this is asking for. The next one says I use a left Riemann sum of 6 subintervals of equal length to estimate this value. This time I have to indicate units of measure. So try that now. 6 subintervals going from 0 to 18. 1, 2, 3, 4, 6. This is 6 subintervals, so I need 6 rectangles. They're of equal length, so all of these are 3, 3, 3, 3, 3, 3. If you're doing a left Riemann sum, I need the function value on the left. So 2.3 plus 3 times, next case, 2.7. And you could take out the 3 in front, 3 times 2.0, 3 times 1.3, 3 times 1.0, 3 times 1.7. Don't go too far and say 3 times 2.1, because this is a left Riemann sum, and since it has 6 subintervals, I should have 6 rectangles. 1, 2, 3, 4, 5, 6. If you multiply that, I actually probably would take this out if I had to do this by hand. And because I've done this before, if you add all these up, because you can see 0.7 and 0.3 would add up to 1 whole, so this would be 5, 7, 8.3, 9.3, 10.3 plus 0.7 would be 11. 33. Let's think about what units this would be though. If I am integrating v of t, I'm going back to position, p of 18 minus p of 0. Remember position, if velocity is meters per second, position must be in meters. Okay, hopefully rolling right along. Now try this one. Got to write Riemann sum, 6 subintervals. You try. I'm going to do it too. This is still the same thing as before, so I'm still going to do 3, but now I'm doing times the right. So I know these are all the same this time, so just like I did up here, 3 for each one of these, I'm going to do 2.7 this time. Going the whole way to 2.1. make sure I have 6 rectangles. It would be 3 times 2.7, so this would be 1, 2, 3, 4, 5, 6. 6 subintervals, 6 rectangles. So this would be 3 times 4.7, 5.7 plus 3 would be 6, 7, 8.7, 8.8, 10.8, right? Because I've done this before, I knew that this is going to be 32.4. What units again? You're integrating velocity, you go back to meters. Okay, a midpoint Riemann sum. Midpoint Riemann sum, how do you do that again? This is only 3 subintervals of equal length. So instead of going the whole way from here to here, I'm going to go from here all the way to here. So instead of 3 and 3, this whole thing would be 6. My mid point would be the times 2.7. So I'm going to say 6 times 2.7. Do the same thing on the next one. From here to here would be 6. My function value in the middle is 1.3. This would be 6. My function value in the middle is 1.7. And again, you can vector out a 6. This would be 3, 4. Add these together, 5.7. And again, we'd have meters because we're integrating velocity. Sorry, this is behind my head. There we go. Okay. I feel like this is all like hanging out with an old friend, just grabbing lunch together. Great times. Except we don't have food and we're doing math instead. Kind of the same. Trapezoidal sum of 6 subintervals. So I need 6 trapezoids. 1/2 base 1 plus base 2 times height. Remember in this one that the height, like when we're talking about these trapezoids, the base 1 and base 2 are the function value. The height is going to be perpendicular to those bases. So my height, if I have 6 subintervals, would be from here to here. Every time it's going to look like this. 1/2 base 1 plus base 2 times height. 1/2 base 1 plus base 2 times height. 3 is the same because these are of equal length. So 1, 2, 3. I need 6 of these. 4, 5, base 1 plus base 2 times height. Oh no, no, I can do it. Base 1 plus base 2 times height. So much room. The base 1 and base 2. So I have 1, 2, 3, 4, 5, 6. There we go. The base 1 and base 2, remember, are the function values. It's like the function value at 1, function value at 2, or in this case, the function value at 0, the function value at 3. So 2.3 plus 2.7. Here, I'm going to take 2.7, because this is my next one, 2.7, 2.0. Next one, 2.0, 1.3. Keep going, 1.3, 1.0, 1.0, 1.7, 1.7, 2.1. Eek! That one didn't look that nice at the end. 1.7, 2.1. I was just going first base 1, base 2, base 1, base 2, base 1, base 2, because you're using some of the same side lengths again, because these trapezoids are right beside each other. If I factor out a 1/2 and a 3 from all of these, I'd have 3 halves. And then you could say 2.3 plus 2.7 plus 2.7 plus 2.0 plus 2.0 plus 1.3. So this is from all of these. I'm factoring out the 3 halves. 1.0 plus 1.2. Should I have just added these up right away? Probably. And then the last one was 1.7 and 2.1. You can multiply all these by 3 halves. You can add them up. And you should get 3 halves, because I'm skipping ahead to this part because I'm already taking up too much room, times 21.8, and you get 32.7. Don't forget about units. I'm integrating velocity, which gives me a position function at. I need to make sure that I'm in meters. Okay, so right now I can see 33.3, 32.4, 34.2, 32.7. Then the last one here, find the average acceleration of this particle from 3 to 9. Okay, so average acceleration. For what value of t in the table is this average acceleration approximately equal to v prime of t? So if I do average acceleration, remember what that is? I take the slope of velocity. V of 9 is 1.3. V of 3 is 2.7 over 6. 1.3 minus 2.7 is the same as 2.7 minus 1.3, but then make it negative, which would be 0.4, but negative 0.4 over 6. And you can keep it like this if you want. Hold on, should this have been 1.4? Yeah. Negative 1.4 over 6. If you wanted to change this, you could do negative 0.23 repeating. That's more than 3 places off the decimal, by the way. But make sure you include units either way. This is just with the calculator, so if you get stuck there. But velocity was measured in meters per second. 9 minus 3 would just be seconds. This is an appropriate estimation, or I'm sorry, appropriate units for acceleration, so you know we're in a good place there. For what value of t in this table is the average acceleration approximately equal to v prime of t? Remember how we estimate the slope of a tangent by doing the slope of the secant? So if I went from 3 to 9, yeah, v prime of 6. If I were trying to find v prime of 6 and I were estimating this, I would do v of 9 minus v of 3 over 9 minus 3. So this is approximately 1.4 over 6 meters per second, because this is the slope of the secant at t equals 6. Oops, sorry, I got there. The other thing is, this you could have done a really long time ago and actually understood this entire page. The only thing that's new from the last couple sections that you've learned is that if I wanted to find the average velocity, and all I'm given is velocity, so average velocity, do you remember how to do that? Average velocity would be 1 over b minus a of this integral from a to b of velocity. So to make any one of these an estimation for the average velocity, we just would have had to multiply this by 1 over, in this case, 18, because this is 0 to 18. Or in this one, 1 over 18 here, multiplied by 1 over 18, or divide by 18. So to get to this average velocity, we could have divided this by 18, divided by this by 18, 18, 18. But remember, all of these are approximations for what the integral from 0 to 18 of v of t dt is. And that is just the net distance, or the change in position from 0 to 18 seconds. Whew. This is so much particle motion. Thanks for learning. Thanks for working. I hope this is starting to make more sense in your head, but if it's not, let me know. Let me help you. Reach out. I want to help. I like it when people understand things if you haven't figured that out already. Let me help you. Okay, I said already weird, I think. Already. Did it lose all meaning to you? Whatever. Okay, have a great day. Double wave. Whoop whoop. Thank you. Bye. I appreciate you.